Hello and welcome back for another lecture. In this lecture, we're going to talk about steel beam design based on bending moment. When you look at the steel, because steel is so much different than wood and timber and concrete, depend on beam, how it's situated, how it's laterally supported, steel the beam design could fall in a different zone. For example, when we did timber and concrete, we try to make sure that we stay below the yield stress. But in steel, we can go beyond yield stress, go to plastic design. If a steel beam perfectly laterally supported, then the beam can reach to its capacity beyond the yield stress, what we're going to call plastic design. And we can calculate MP based on that. Or there are cases that when you have a steel beam, ladder is not supported, and it may reach the failure before it can reach its capacity. So we're going to do about 3-4 different examples, go through all these different zones to kind of explain this. So we got this beam, wanted to select a beam for this particular situation here. The clear span is 30 feet, and we have a live load down in the middle at 15 feet, and then a dead load of 1.5 kip per foot. Fy is 50, and this is fully laterally supported, so there's not going to be any lateral buckling issue. So the first thing we're going to do is we're going to go ahead and calculate the load both in load resistance factor design and in ASD. So WD is 1.5. We're going to use load combination number 2 and in LFRD, as you can see on the board. So I'm going to have back up for that one, come back. And this is bothering me right here. I got to clean that. I'm just perfectionist. I'm sorry. It's okay. Don't be sorry. Be happy. All right. So now when we look at the load, the dead load is uniformly distributed load, which is the unit is 1.5 kip per foot, and the live load is concentrated load. And therefore, we're going to go ahead and make sure when you calculate this, they both have the moment is calculated different. So first, we're going to go ahead and calculate the load in LFRD. And WU in here, it's going to become 1.2 times 1.5. And that comes out to 0.8 kip per foot. And that's for dead load. And for live load, we have for the live load, we're going to have PU is equal 1.6 times 30. And that comes out to 48 kip. Now I'm going to calculate my moment, MU. And based on beam formula, you got to be careful. So we're going to have WL squared divided by 8 for the uniform distributed load. And for the constant load, it's going to be PL divided by 4. I have W come 1.8 multiplied by L squared is 30 squared. Divide that by 8 plus P came out to be 48 and time L is 30. Divide that by 4. My MU come out 562.5 foot kip. So this is LFRD. Now we're going to move over to ASD. In ASD, you basically just combine both load. You don't have to multiply by any factor. So your load is going to basically be WA. It's going to be 1.5, and PA it's going to be 30. PA is 30. Moment, it's going to be the same thing. It's going to be WL squared, so W is 1.5, and L is 30 squared divided by 8 plus PL divided by 4. P is a 30 times 30 is a L divided by 4. So my MA comes out to 393.8 foot kip. So what we have here is the moment based on applied load, based on our load. We're going to take this moment, then we're going to go to table 3.2. We're going to look in table 3.2. We're going to find a moment, the capacity of the beam, a capacity which is bigger than this in LFRD and bigger than this in ASD. And then once we find that, we can go ahead and find a beam size for it. So take a look at table 3.2. And from table 3.3-2, and we look at the phi b time MBX, and we can see if we look at the W24/62, and that one has the phi b MX of 574. That's a foot kip, and that is bigger than this one, so this one can do it. So now we look at the same table and look at the MPX divided by omega b. Excuse me, for W20, we were looking for something, a number bigger than 393.8, and we're going to see 399. So from 399, we can say, okay, let's use W21/68. So if we use W21/68, and we will have the our moment, MPX divided by omega, comes out to 399 foot kip. And that is, again, bigger than our applied moment, and that's what we want. Now remember, when we calculated this loading, we did not consider the beam weight itself. So now we're going to go ahead and here, we're going to go ahead and incorporate the beam weight, and we recalculate our moment, and hopefully it comes out less than the capacity moment of the beam that we have selected. So basically, because the dead load is a uniform distributed load, we're going to go ahead and add, in here we're going to add 62 pound per foot, and in here we're going to add 68 pound per foot, and then we recalculate. Okay, so our WU comes out to 1.2 times, we had 1.5 plus 62 pound, 0.062, and that comes out to 1.874, 1.874, and our PU stays remain the same, no change. Therefore, let's go ahead and calculate our MU, because I'm going to call MU here for. So MU, it's going to come out to WL squared, which is going to be 1.874, 1.874 times 30 squared divided by 8, plus PL is going to remain the same, 48 times 30 divided by 4. So my new MU come out to 70.8 foot kip. So now we have 570.8 kip. That's our applied load, bending moment based on applied load, including the beam weight, which is less than the capacity of the beam that we have found from table 3.2. Therefore, it's good. We can say, okay, 570.8 is less than the capacity we have from table 3.2 for beam W24/62. In this case, it's 574. That checks out. So now we're going to go ahead and do the same thing here. And So our WA is basically 1.5 plus 0.068, and therefore my moment is going to be calculated the same way with increased uniform distributed load. So MA comes out to 1.568 times 30 squared divided by 8 plus PL divided by 4, which is 30 times 30 divided by 4. And that comes out to 401.4 foot kip. Now you look at it and you notice that, okay, when we pick the beam size, we pick 399, and when we add the beam weight to it, our applied load, our bending moment due to applied load, including the beam weight, came out bigger than the capacity of the beam, the allowable capacity of the beam, which was 399. So therefore, we says, okay, that's no good. Let's pick it up one more time. So we're going to say this is no good. And we're going to go ahead and select something bigger from table 3 point. Because this is didn't make it, we're going to go ahead and pick a bigger size. Let's use, okay, cross this out. We're going to go W 24 by 68, and our capacity is 442. So the capacity comes out to, let me cross this out. It became 442, which is bigger than this one, and therefore we say, okay, 442 bigger than 401, we okay with W24 by 68. We're going to go ahead and move on to the second problem. Sometimes if you have a hole in the beam, of course, you have to worry about a reduction factor. Take a look at, I'm going to bring this up multiple times, this section of the spec F13. It talks about there are some requirements we have to satisfy to calculate our moment. So in here, in this case, we have the beam, and the beam is W24 by 176. And if you go to table 1.1, it's on the screen, get all the information out of it, whatever you need. And then we have our spec is a FY 50 KSI, and FU is a 65 KSI. So what we're trying to find out, question number A for this question is, if we have two holes in the beam with a 1-inch bolt going through it, what is the reduction, or what is the capacity of the moment, phi b times MN in LFRD, or MN divided by omega in ASD. So how are we going to do? First thing we're going to do, we're going to go ahead and calculate the tension flange, which is the top here, the gross cross-sectional area, and then deduct the hole. First, we're going to go ahead and calculate the gross cross-sectional area of the flange. So this is going to be AFG. Let's retire this marker. That's no good. Remember, be careful. Don't use the area for this whole thing. We just want to look at the area of the tension flange, which is basically BF times TF. So BF times TF, and then minus, actually that's it, which is equal, we have 12.9 multiplied by TF came out to 1.34, and that comes out to 17.29 inch square. Now I'm going to go ahead and calculate the AF net area, which is that 17.29 minus, I got two hole, 2 times, it's a 1-inch diameter bolt, so it's going to be 1 plus 1/8, and then multiplied by the multiplied by 1.34. So that, okay, so now we have both of those, And the next thing we're going to go ahead and we're going to look at the spec again. Next thing we're going to go ahead and calculate is the FU time AFN. I'll read this down. And that comes out to 65 KSI multiplied by 1427. So that, and that's going to be in KSI and inch, so it's going to be kips. I want to do just like that. Let's find out if it's we're going to satisfy the requirement for YT. So Fy divided by Fu, Fy divided by Fu, and that comes out to 50 divided by 65, which comes out to 0.77, and that less than 0.8, and therefore we can go ahead and say YT, it's going to be equal 1 in this situation. Otherwise, it would have been 1.1. And then we're going to go ahead and satisfy the other requirement on the same F13. We want to find out that our FU time FAN, which became out 927.6, is that bigger than YT time FY time AFG. That's a node number B or node number A. So which one is going to satisfy? So we're going to go ahead and calculate that. That's going to become a YT came out to 1, and then we have actually let me write this down. That way we know what we're doing. YT time FY time AFG. So it's 1 time Fy is 50, and AF was gross cross-sectional area was 1729. So that comes out to 864.5. 864.5 kip. And then we look at the spec, and the spec tells us that's bigger, and therefore the limit state of tensile rupture does not apply. So it really doesn't reduce it that much. Okay, so 2 bolt is okay, it's allowed. It doesn't reduce it too much. So now we're going to go ahead and solve the problem. Let me erase this section here. Because we satisfied condition A of the spec in section F13, therefore it says right there, let me read it to you. It says the limit state of the tensile rupture does not apply. So we're going to go ahead to table 3.2. Therefore, from table 3-2, we're going to get all the information for W24 by 176, which is basically phi time M PX comes out to 1920 foot kip, and that's for L RFD. And for ASD is basically from the same table. You can find out MPX divided by omega B, and that comes out to 1270 foot kip. We don't have to calculate that. Engineer, we smart and we lazy at the same time. That's why we came up with these tables. So we just go ahead and go to the table and we take it out. And these are capacity of this beam. The way it's loaded with those bolt hole in it. The capacity of it did not change. Therefore, we take it out from the book itself, table 3.2, and that's where they are. So now let's go ahead and go to second part of this problem. What if instead of 2, we're going to make this 4? Let's go ahead and put another bolt in someplace in here. Okay, and I'm not doing a good job, but let's say there's going to be one right here too. And so what if we make it 4? So we're going to do the same problem with 4, see what happened. Let me erase this. Okay, again, we're going to go ahead and satisfy the requirement section F13 of the spec. And it's on the board. So I'm going to go ahead and recalculate all that stuff. We already calculated the gross cross-sectional area, came out to 1729. I'm not going to go ahead and do it. So I'm just going to go AFN, which was 17.29. We got 4 bolts. We're going to be minus 4 times 1 plus 1 over 8. And the thickness is 1.34. 1.34, and that comes out to 1126 inch square. 11.26 inch square. So after we found that, but based on the same requirement, we already know that our Fy over Fu came out to 0.7, and our Yt is still not going to change. That's going to become 1. And then we're going to find out our Fu time AFN, and that comes out to 65 times 1126, and that gave us 65 times 1126, 731.9, 731.9 kip. At the same time, we want to know what was Yt time Fy and time AFG, and that's the same as before. I'm not going to write it down, which was 1 plus time 50 time 17.29, and that came out to be 804 kip. And looking at the section right there, it says that Fu time AFN, if it's less than this, then B will apply. And the B says, so there's going to be F13 section B will apply, which, let me read it to you. The nominal fluxual strength Mn at the location of the hole in the intention flange shall not be taken greater than Mn is equal Fu time AFN time SX divided by AFG. And you know that SX from table 1, we know that we have everything right there, so let's go ahead and fill it in. I got 65 multiplied by F came out to 1126, and multiplied by SX from table 1, it came out to 450. That's an inch cube anyway, and that's an inch, that's an inch, that's so very good. And AFG came out to 1729, 17.29. So now I have MN comes out to 1904. 19,048 inch kip, but I want to make that to a foot kip. It's not good enough for us. So let's divide this by 12, and that comes out to 1,587, 1,587.4 foot kip. So now let's find out, now we have that, want to find out what's the capacity in load resistant factor design and in ASD. So for allowable stress design, it would be, for a lot of D will be, let me just make a line here for us to get this answer. It'd be phi B time Mn, and that's equal 0.9 time 1587.4, so which comes out to 29 foot kip. And in here, it's going to be basically MN divided by, and that is 1587.4 divided by 1.67. And I get, and that one, 951 foot cube. Now remember this. This is the capacity of that W24 by 176 if you have 4 holes in it in the top flange right here. And that's what's going to reduce it to it. However, if we had 2 holes, the answer was before, what was it? Let me see if I remember. This was 1920, and this one was 1270. That's a huge reduction. So when you put a hole in beam, it does reduce it. So this was a good example. Okay, we're going to go to the next example. This time we have a beam is 35 feet long. Dead load is 450 pounds, and life load is 750 pounds per foot. The steel is FY 50 KSI. And the life load deflection limit is given to be L over 360. And also the architect says that the depth should be 18 inches. So basically we got select W18. Kind of limit us. So go ahead, let's get to work. First thing we're going to do, we're going to go ahead and calculate the load. And that's based on, we've seen this before, based on AAC chapter 2. So I'm going to have WU is equal 1.2 times 450 pound 0.45, make that cube per foot, and plus 1.6 times 750.75 kip per foot. And so W, you're going to come out to kip per foot. So for ASD is basically different. We're just going to add those two up. It'd be 0.45 plus 0.75 kip per foot. Now, we have calculated the load in both load resistance factor design and allowable stress design. Now we're going to calculate the bending moment. We're just going to go ahead and use table 3-23 or the beam formula. Take a look at it on the table right there. So from table 3-23 case A, case 1 actually, we have mu is equal WL squared divided by 8, and the reaction is WL divided by 8, and then with deflection. We need all those three for now. So let's calculate the mu. Mu comes out to 1.74. This is not including the beam width here. Time the length is 35 square. Divide that by 8, and that comes out 166 foot kip. We're going to do the same exact thing. It's going to be MA is equal WA L squared divided by 8, and our WL came out to this. And so we're going to have a 1.2 times 35 squared divided by 8. That's not good. Comes out to 184 foot kip. So remember, this is the bending moment due to the applied load. So now I would like to find out what's L over 360 is here. So I got L over 360, and that comes out to, let me use a different marker here. L over 360 comes out to 35 times 12 and divide that by 360. So I'm having a marker issue here, be patient. And L over 360 comes out to 1.17 inch. So that's our deflection limit. And if we go back to the same table that we looked at the beam formula, we can look at the deflection, and the deflection, which is delta max, in our case is equal 1.17, and that is equal 5WL by power 4 divided by 384 EI. 384 EI. So we want to know what I it's going to come out. And basically, I kind of come out, IX is equal 5W, that's a life, L by power 4, divide that by 384 E delta max. And so we can calculate our moment inertia, and therefore that's going to come out to, okay, from here still, 5 times WL came out to 750 pound per foot. Okay, 750 pound per foot, and L came out to 35 feet by power 4, and divide that by 384. E is 29,000 KSI, and delta max came out to 117. So our 746 inch by power 4. And our IX came out to be 746 inch by power 4. Let me take this out. I need this room here. And you know how we got this. So now we found that if you go to table 3-3, from there we can pick out the from IX. We can pick out the our W18, because we have to pick out 18. We limit it to 18 inch, and we can pick out W18 by 50, which has an IX of 800, and that's more than 746 inch by power 4. So this beam is compact because it is laterally supported, and section F2 applies that. And we're going to go ahead to table 3.2. From table 3.2, we're going to go ahead and calculate the phi times MN, which in our case is the same as a phi times MPX, phi B MPX, and from that table that equal 379 kip. 379 kip, foot kip. And this 379 foot kip, which is the capacity of this beam that we just selected, it should be more than that, and that's good. Then we say, okay, 379 is more than 266. Okay. This is in load resistant factor design. So if we look at the same table, 3.2, we can find out the next column, MN divided by phi B, divided by omega B, which is the same as MPX divided by omega B. And that came out to 252 kip. 252 foot kip. And that load is more than our applied load. 252 more than our applied load, which is 184, then we good. Now, one thing you remember, we use the table 3-2, shortcut, bang. Engineers are very smart. They make this table for ourselves, and we go pick it out. So if you don't feel like that, same section F2, take a look at it. We can use that same F2 to calculate the plastic moment. So let's do it the other way, just so you know for yourself. We know that our beam, we selected W18 by 50, so ZX for that from a table 1, or from a Z table, whatever, you can go ahead and find out that 101 inch cube. Equation, our Mn is equal plastic moment is equal Fy times Z. So my Mn, or which is MP, comes out to 50 KSI. Multiply that by what was Z? 101. 101, and that gives me 5,050 inch kip. I want that in foot, so divide that by 12, and that comes out to foot kip. So coming back in here, we're going to go ahead and we're going to say our phi Mn right here, basically, which is equal phi b MP, and comes out to 0.9 multiplied by 421, and that comes 79. So that's where we got 379, which is bigger than 266. We're good. So this is just two different ways calculating it. Coming back in here, we say, okay, Mn divided by omega, and that was 421 divided by 1.67, and that should come out to 252. Okay, so we have another example here, and we have this beam is 34 feet long, and it's braced at the end and at the center. So basically, the unbraced length is about 17 feet, and we have a dead load and live load given to us, and we want to find out what size beam should we select for this. One of the first things you want to do calculate here is you want to find out what is a CB, because we're going to be using table 310, and in the table 310 we need to know what the calculation of CB is. To find the CB, then we're going to go to see from the chart, CB comes out to 1.67 here. Go ahead and calculate our applied load. Let's make a chart here. Say this is ASD load resistance factor design. So we have 1.2. That'd be PU 1.2 times dead load is 30 plus 1.6 times 40, and PU comes out to 100 kip, and from a beam table, our MU comes out to PL divided by 4, which is equal 100 times L is 34, and divide by 4, and that comes out to 850 foot kip. So now we have that. We're going to go do the same thing on over here. It's going to be 30 plus 40. PA is equal 30 plus 40. That's 70. MA comes out to PL4. So 70 times 34 divided by 4. And that comes 595 foot kip. So now we have found out what is our bending moment due to applied load. From here, we're going to go to table 310 and take a look at table 310. We're going to go to table 310. From table 310, we have to use LB and moment. But you got to remember here, before we do that, our CB came out to 1.67. Therefore, we have to adjust our moment. And to do that, we have our moment came out to 850. Effective comes out to 850 divided by 1.67. This is a 1.67 here. So that comes 509 foot kip. And we're going to do the same thing for the other side. And that's going to be basically MA effective, which is 595 divided by 1.67. And this 1.67, please don't, that's what it is. It's not that omega. And that comes out 356 foot kip. So now we have that. Then we can go to table 310. And we're going to say, okay, CB is equal 1 because we made and we change our moment. And we make a vertical line from the LB is equal 17 all the way up. And then we go to in load resistant factor design moment section. We're going to find 509, and we make a horizontal going all the way across. Now the highlighted area, which is to the right and upper corner, and we can select any beam from there. So let's try to select any beam closest to the intersection. And first, let's try W24 by 76, W24 by 76. And when we do that, we go to table 3-2, and we're going to find out phi b times MPBX comes out to 150 foot kip, which is less than 850. So this one came out no good. And let's try another one while we're there. So we're going to go ahead and try W from the same line. Let's pick W27 by 84. W27 by 84. And that's from the table 3-2. It's going to give us our phi b MPX come out to 915 foot kip, which is bigger than 850. Now, this is cutting a little bit close. If you don't feel comfortable, you can go ahead, calculate your load, add the weight of the beam, and then recalculate, see what's going to work out. Normally, if you pick a bigger size, you don't have to worry about that. Okay, so now we're going to go to ASD part, and we're going to do the same thing. We're going to try W24 by 84, and from a table 3-2, we're going to find out that MP divided by omega comes out to, and that is less than our applied load 595, no good. So let's pick a bigger size, we can just pick something bigger than this one and probably work out. So let's take 27 by 84 and see if that comes out. 27 by 84, and that's from the table 3-2. Our MP divided by omega comes out to become, oh, that's not a good 6 and 9. And that's bigger than 595. It's kind of close. You can even pick another bigger size, so your margin is a little bit bigger, depending how you design and how comfortable you are with your design. So this is basically how it's done.